Yeah, as Cindy said, thanks for joining us today. I know it's kind of the end of the year and things are winding down for everybody at the end of the semester here. Um, but yeah, so today's topic is sort of the third installment in the batch computing series that we do as part of the complex program, and it's focused on sort of an introduction to high throughput and sort of many task computing and sort of how those are different than sort of traditional HPC. So the slides with the talk will, as I mentioned, we'll go through and sort of discuss the general definitions of sort of high throughput computing, many task computing, and then talk about some of the strategies and different techniques that you might use to sort of put these types of workflows together. And then we'll jump into sort of demonstrating some of the exercises that you might be able to try out on a system you have access to. There are some links here that we'll probably come back to later once we're done with the slides. The first one is just the the actual excuse me complex PDFs. So Cindy put a link to this specific talk in the chat. Excuse me one second. We have a GitHub repo where many of the different complex talks have exercises posted in the GitHub repo there. And then specifically the most recent series of exercises for this talk were actually at our SDSC Summer Institute back in August, and that was sort of the last time I had time to really clean up some of those exercises, and I haven't actually translated them over into the complex GitHub. So that's where you'll find the exercises here if you have to leave early. Okay, excuse me. Sorry, I've been a little bit under the weather, so I'll try to keep my crud to a minimum today. Okay, let's go ahead. So, I assume hopefully this isn't your first time necessarily at one of these complex talks, but just for general overview, if you're new to the complex program, it's a new training program that we started at SDSC about a little over a year and a half ago, almost 2 years now, where we try to cover the essential sort of skills that you need to use supercomputers that go beyond sort of any sort of like necessarily like programming, like writing code and that you would need to run on these systems, right? Sort of all the ancillary skills that are around these that you need to understand to effectively utilize these resources, like parallel computing concepts, like the different types of Linux tools that you'll often want to use, some Bash shell scripting, and data management. And so there's a whole series of talks. We have, I think, about 13 or 14 different uh, uh, sets of materials for different topics that you can find in our repositories. Okay. And the whole goal of Complex with this approach is really to transition newer users to advanced cyber infrastructure and high performance computing resources from your sort of laptop or desktop that you might be working on most of the day to when you need these larger resources with more compute and more memory and need to scale up your sort of research workloads. Okay, excuse me. As I mentioned, this is the third talk in the batch computing series. So I have here links to the two previous ones. If you haven't been able to attend those talks, there's recordings and slides and exercises associated with them. Might not be as well organized as we would like yet, but I mean, all of the material is available online, either in the GitHub repos or in the archive of the recordings and the slides. So for the talk today on high throughput main task computing, the goal is really to cover the general concepts of high throughput computing, many task computing, how they're different from traditional high performance computing workloads. And then what we want to talk about is some of the key structures that you use to start constructing these types of workflows, in particular with the Slurm workload manager. And so we'll talk about Slurm job arrays and Slurm job dependencies, and a couple other things like job bundling as well. This is the table of contents for the overview of the talk. So again, we'll start out with some brief definitions. I'll do a quick review of sort of the key things that we covered in the job scheduling talk with Slurm, which was the last talk in this series, just in case you weren't here. And then jump into the general ideas of job arrays, job dependencies, and job bundling. And so then cover a few other things like different resources that are out there for high throughput computing, and other types of workflow managers that make the many task computing problem a little bit easier and are pretty popular out there that you can go into. And then we'll jump into some, as I mentioned, the demonstrations of the exercise, and then Q&A. Okay, so high performance computing, right? So traditional high performance computing really focuses on problems like this, where you have let's say, a large physics model that you want to simulate something on. In this case, weather simulations, right? There's key advantages for doing these types of calculations on supercomputers, right? That you can leverage the large amounts of compute and memory to either speed up a problem and solve it more quickly, right? So you might have this, lower resolution simulation if you need to run it faster, right? You can get higher fidelity and solve larger problems. That's larger, more complex problems if you need that sort of higher resolution. Or you might need to solve many variants of the same problem over and over again. So say on this third example, to get sort of a statistical distribution of, say, the track of the storm as it comes in and makes landfall. Right. And so these are sort of the key advantages of leveraging HPC for these sort of traditional types of problems. And just to step back on the fundamentals, right? How do we leverage those resources in the traditional sense? Well, you have some sort of problem, like the weather simulation problem. That simulation could be run serially on a single computer processor or core in a serial manner. But the systems we have today are like multi-core, multi-socket, highly parallel, even at the node level in the HPC clusters that we have today. And so to take advantage of all those resources and across multiple nodes in these systems, you can break up these problems, especially these physics-like problems where, like in a weather simulation, the different boundaries of the problem are really physical. You can break up the geography and put different parts of the geography across different parts of the compute resources, right? And have individual processors focus on individual sections of that geography in that weather simulation, right? Where you have instructions that are mostly independent, that can be run across that section of the problem, with some interconnecting instructions that communicate data between the different processes that you need to communicate as you, say, update the weather simulation as it runs in time, right? That's sort of the traditional HPC type of workload as you scale things up. High throughput computing is a little different, right? It really aims to solve a problem. The problem can be large, but usually this problem is made up of many similar, usually smaller, independent subtasks without a lot of communication, or hardly any between these independent subtasks, right? So the most natural type of problem is these embarrassingly parallel problems, where are kind of the most natural fit for high throughput computing systems, right? And example problems include things like batch processing, An example there you might think about is, as you use your credit card, right? That transaction is getting communicated back to the credit card company, and many of these banks and credit card companies, right, are running real-time analytics on every transaction, right? If you've ever gotten a notification of, oh, did you make this purchase? Because we thought it looked suspicious, right? Those tiny transactions that you're making, that little data that you're generating from your purchases and the millions of purchases across many, many people, right, need to get sort of processed in real time as fast as possible, right? And they're solving that larger problem of trying to prevent, fraud in the system by processing these very small independent subtasks all along the way to ensure the security of the payment network, right? So that's sort of a batch processing example. Brute force search, maybe you have lots of data that you need to go search through, right? Lots, so you can divide up the chunks. It's very embarrassingly parallel because you usually can search through those different chunks of data independently, and you don't need to know about the other ones, right? Monte Carlo simulations where you're doing lots of iterations of the same simulation over and over again, but you need to generate that variability in the system to get some statistical results at the end. One of these examples is shown here with the ice cube detector at the South Pole, which is a particle physics experiment. They did a pretty big experiment a few years ago using a bunch of cloud GPUs to run Monte Carlo simulations on how the particles generate the light and interact with the ice and generate light that then hits their detectors, right? And by running many, many simulations over and over again, they're able to improve the actual model of the ice around their detector, right? Which improves the sensitivity of the measurements to the sort of astrophysical particles that they want to study, right? So those are just some types of high throughput computing problems that are sort of out there, right? Where there's this overarching general goal, big problem that you want to solve, but there's many similar or almost exactly the same type of problems just needs to get solved over and over and over and over again, either as quickly as possible or just consistently over time as the project progresses, right? So hopefully that sort of lays the groundwork there for how that's different than high performance computing necessarily, right? Because many of these applications are just, can be either serial or usually, low amounts of shared memory, a few cores, a few gigabytes of memory. You don't need a ton of resources for some of these applications, right? You just need to leverage a bunch of resources over time on sort of small programs with small problems that add up over time. Many task computing is back a little bit more in the direction of HPC. And it's not a term that people use a lot, but it really highlights sort of the complexity of um, research workloads in general, right? Right, because most of your research workloads, while you might even just have a large, the main sort of compute problem is a real big weather simulation, or in this case, like a fire simulation, or both. Um, there's a lot of other like tasks of different complexity that need to get coupled together to make a final product, right? A final research product, or in this case, like an operational product, right? In this case, this is a fire modeling workflow here at SDSC with this Wi-Fi project, where they take weather forecasts, real-time sensors, take all that data in. They have fire models and weather models to help predict how wildfires will spread, right, in real time, essentially, right? And so it's a problem that you need to try to solve quickly to get operational predictions for the actual first responders. But you can see here, like, there's sort of sensor data that gets dumped into databases, weather forecasts that get dumped into database, those things get assimilated into the fire models and to the weather models that are trying to predict what's going to happen, a couple hours out, and make some sort of um, guesstimate of what's going to happen with the fires, right? And so the scale of the different sub problems here can be wildly different, right? But it's this coupling of these different subtasks together that gets you that sort of final outcome, right? And so this is just sort of the in between you might have some high throughput like elements in the many task computing workflow. You might have some HPC type elements, and by coupling all of them together with inputs and outputs from each step along the way, you're able to solve a practical problem um, by linking it all together, by creating these workflows. And that's really what this talk is about, like trying to show you how you start to couple different jobs together as you schedule them on these resources to create workflows like this, or if you just need more simple high throughput workflows. But at the end of the day, we're all doing a little bit of many task computing usually too. Okay. So, quick review of just job scheduling in general, which we talked about last time in this series. Um, Again, this is an example architecture of expanse at SDSC. We have, the different compute racks. Every compute rack has nodes. Every node has multiple processors. There's lots of complexity. There's different file systems. But um, we like to use in complex sort of this conceptual model of the things that are going on, right, in an HPC-like system, where you have login nodes, that's sort of your front door that you get into the system. There's management nodes that actually run the HPC system, right, that manage the compute nodes where you run your workloads. There's the different file systems that you interact with. And the job scheduler, right, lives on those management nodes, basically, that oversees how you, when you request resources from the scheduler, right, it'll decide where your jobs are going to run, right? And so this is just the general landscape of the conceptual model of the different pieces that we need to remember that are on the system. Okay, so just as a reminder, a batch job is just a prescripted set of commands that are executed as processes. These can be multi-process, multi-threaded, uh, um, jobs. But at the end of the day, it really is every job script that you write is just a shell script. So if you have done some shell scripting, right, you can write a job script. And all it does is add in the elements of the resource request, right? Basically, after you make all of the request of how many compute resources, memory, and time you want on the system, all you need to do is write out the actual commands that you want the scheduler to execute on the resources that you've requested, right? And it really is kind of this, the scheduler itself is really kind of like the air traffic control of the system, right? You write the job script because that's sort of your flight plan. This is what you want to happen. You submit that job script, that flight plan. Your job goes in the queue and waits to take off. The scheduler, once it's ready and finds you a spot where there's enough resources and enough time, and use other factors like the priority of like who needs to go first and next, will launch your job on those resources, and you'll get back the output results, right? It's this batch processing workflow. And the most common workflow manager out there is Slurm, right? And we learned in the last talk kind of the essential Slurm commands of sbatch. That's what you use to submit the job scripts to the scheduler. SQ allows you to sort of view the jobs in the queue. So is your job running? Is your job waiting or pending to run? You can view information about your jobs there. And then scancel if you make a mistake in your job script and need to cancel things. Scancel is the way to take your job out of the queue, whether it's running or pending. And these are the exercises you can go back to in the batch computing uh, talk. And again, I think I've just covered this. The structure is really, it's just a shell script. You have your S-batch resource requests, attributes that tell Slurm what you want. Like, and some of it's just informational, like the job name. It's just, this is the name you want to call the job, which might relate to what the output files look like. You got to charge every job to a different account. There's different partitions and things that we talked about in the last talk, and then you request sort of the resources, and then you run your commands. Right. This is the general structure of of a job script. Okay. So that's sort of the um, initial definitions of high throughput computing, mid-task computing, and then just a quick review of the job scheduling with Slurm we talked about in the last talk. So there's three sort of practical um, topics that are covered in the exercises. So I don't have a lot of material in the slides. I'll just go through the definitions, but there's three of them. There are sort of job arrays, job dependencies, and job bundling, right? And I'll explain what each of those are in the next couple slides. So job arrays are a structure that you can use on basically any batch job scheduler will have job arrays built in. I don't know any that doesn't. Um, but what it allows you to do is essentially take your job script and just add another attribute to it that allows you to launch multiple versions of that job on the same system, right? So basically, if you were like in our first example there, we were requesting one basically CPU core and 1 gigabyte of memory to run that example one job, right? There is in Slurm and other schedulers another attribute that you can request uh, it to run as an array, where in Slurm that it's the sbatch dash dash array directive. And here in the example, I'm labeling it equals 0 through 9. So basically, I'm going to run 10 versions of the same job if I add that line to my job script. So it will run 10 identical copies of that same job script, right? And that's allows you to launch these, obviously, hopefully it sounds like this is ideal for sort of the high throughput computing case, right? Where if you need to run a Monte Carlo simulation and just run the same thing over and over again with just a slightly maybe different input or random seed number to start, right? That's sort of the natural type of job that you would run as an array, right? There are also, when you start using arrays, in addition to, as you might remember, every Slurm job or basically any job in any scheduler, right, is assigned a job ID, right? When you start using arrays, there's not only the job ID, but there's sort of the array ID and the array task ID that also can be used as variables in your job scripts to understand, like, hey, if you had 10 input files here, right, you could use those index numbers like 0 through 9 as a hook into, like, hey, if you are job 0, please read file 0, right? Dot text or whatever, right? If that's your input file, right? So there's ways to use these indexes on the arrays to manage inputs and outputs and other types of variables that you might use. And those are shown, some examples, sort of somewhat contrived, but um, just simple practical examples of how to use these things in the exercises we'll talk about shortly. Okay, so that's job arrays. So it's really if you want to launch identical copies almost of the same job, right, with very little difference other than maybe inputs or slightly different um, conditional parameters that you might want on individual jobs. Okay. So yeah, this is when we get to the exercises, I use a simple sort of Monte Carlo program that calculates an estimate of pi. So that's what is used in the exercises. So we'll skip over here. But if you need to come back here for reference, it's just I don't know what else to say here. Yeah. Anyway, we'll talk about it when we get to the exercise. Job dependencies. Okay. So after arrays, usually, I use arrays a lot in the type of work that I run, just because I'm usually running a lot of benchmarking on our systems to, check if like, if our system administrators have like replaced like a CPU in like one of the nodes, we need to just check that it's working as it should. So we run some standard benchmarks on that against some of the other ones and just double check that everything looks similar. So I'm usually, gathering a little bit of statistics, and so just running the same job over and over and over again. Job arrays is very easy with it. When you start thinking about sort of the many task type of computing, where you have, maybe you have an array that you want to launch. You launch your array, you have your Monte Carlo simulation, you generate all these results, right? Well, usually after you generate all those results in that type of workflow, right? Usually you need to reduce those results into some sort of collective results, right, from all the simulations that you ran. And so that's like another task, right? And that could just be one other job, it could be many other jobs. It sort of obviously depends on your workflow. Um, but you can see, like, if you know what all those tasks are in addition to whatever you ran in the array and maybe the Monte Carlo simulation, um, you can then you should be able. I mean, that the reduction job maybe after the simulation, right, needs to happen after the simulation, right? So there's a dependency there, right, in time and in ordering between the tasks in that simple sort of two task workflow, right? And so there are ways to link those two within the scheduler so you can actually submit all of them with and all the jobs, no matter what they are, arrays, not arrays, but you can link jobs together through dependencies, right? To create a sort of uniform or a unified workflow, all in one submission, essentially, right? so, so that's all job dependencies are, right? It really is just like you can explicitly um, tie different jobs together. Usually it's based on, in case of Slurm, right? It's based on job IDs. And there's a different types of dependencies that you can set up. The most natural one, which is the only one I've listed here, is this after OK, right? So basically it's like, if you submit a job with a dependency, right, you have to choose one of these conditions essentially, right? And so it's like if I make this job dependent on job ID 0 and I'm going to be job ID 1, well, I can't run, tell the scheduler I can't run unless job 0 completes successfully, right? So there's different conditions and things you can set on the dependencies. There's, I think, maybe 6 or 7 in Slurm, but honestly, I've only really ever used this one myself, but there are cases where you can use different ones. But yeah, this allows you to sort of start building these more complex workflows with these distinct computational tasks, right? That's sort of the idea. So it's sort of ideal for this many task computing case. Okay. And the third strategy that you might use is job bundling, right? So what is job bundling? So usually this occurs when you are working on an HPC a resource that only lets you schedule jobs at the node level, right? So if you have a high throughput computing workflow or like that is like a bunch of serial jobs, maybe you need to launch like a job array with like across 1,000 cores, but every job is just going to use a single core and a couple of gigs of memory, right? Um, on systems like Expanse at SDSC, we allow those jobs to run on individual cores with a few gigabytes and things like that. That's right. We allow users to run in sort of shared nodes is what we would say, right? Where there's multiple users with multiple jobs all running on the same node because all these nodes have many cores available. So it's a shared computing environment, right? There's other people's jobs on the same node at the same time as yours, right? And a system like Spance, you can actually launch those, say, job arrays with a single core and let it go. On other systems, they don't allow you to do that, right? You have to, if you request a resource, it's at the node level, not at, say, the core level, right? So you have to figure out if that's where your compute time is and well, your problem doesn't quite match what their sort of expected workloads are, right? Because if they want you to schedule at the node level, they're usually expecting you to use the whole node fairly easily or scale out across multiple nodes, right? So you just might be on the wrong resource. But there's many cases where you just end up with compute time on different resources, and this is what happens. So job bundling is the idea of how do you manage these smaller computational tasks within a single batch job, right? And so that you don't waste the resources, right? Like, for example, on Expanse, you have 128 CPU cores per compute node, right? The standard sort of compute node. If you were given 128 cores, but your code is not parallelized, but you can run thousands and thousands of copies of it pretty, to get good results, how do you write a job script that allows you to use that whole node, but run those single core jobs within it efficiently, right? So that's job bundling, or some people might call it job packing too, right? Because you're trying to pack those, the execution of those smaller programs inside a single job, right? And there's multiple ways to do this. The fundamental problem is that it's all fairly manual, right? So you have to kind of figure out what technique you like and what works for you. I personally am not a fan of job bundling. I try to avoid it. And especially on our systems when I'm helping users, since we allow shared level or shared node use, I usually tell them it's like, I'll come across someone's script and they're definitely doing basic job bundling. I'm like, you don't have to do that on our system. It's you can actually make it everything a little bit more cleaner and anyway, job bundling gets a little bit messy. But I touch on in the examples, or at least in the discussion there in the online material, of the different techniques and of how to get started thinking about it. And we'll talk about that in a second once I get to the exercises. Okay. Okay. So those are kind of the three main sort of practical strategies that sort of touch on what you might need to do in the case if you have a high throughput or many task computing workflow. And those are kind of the three things to learn how to use. But there are, if you do have a high throughput computing problem, there are dedicated resources out there that are sort of intended for this type of problem, right? And so I just want to touch on two of them, which are somewhat related in this distributed high throughput computing resources. So one resource out there, if you're not familiar with, is the Open Science Grid. So the Open Science Grid is this sort of distributed compute network that allows you to sort of run for free, essentially, right? So the Open Science Grid, they have what's called the OS pool. You can get a count there. And you can see here the ideal types of jobs that they say you can run. And it uses, they don't use Slurm, they use a different scheduler called HT Condor, which is it was designed originally for this sort of high throughput computing use case. And so it's got a lot of functionality around the high throughput computing job like workflow. And they also have their own sort of workflow management stuff where you can construct the dependencies between the jobs a little bit more easily than you can in Slurm. So there's a lot more features for the sort of many task and high throughput computing like workflows. If you have one of those, HD Condor is actually probably a better scheduler for that if you don't have large multi-node simulations somewhere in the workflow. But yeah, so it's really meant for smaller jobs with short amount of time, not too much memory, not too much input and output. This is kind of the ideal jobs there, right? And um, yeah, it's a really great resource, and the people there are really helpful. And so if you're interested in if you have high throughput computer like problems, I would definitely recommend checking out the Open Science Grid. Another resource that's out there, which is more in line with a traditional access CI system, right? So a system like Expanse is allocated through access, the NSF sort of uh, advanced cyber infrastructure umbrella organization that manages sort of the allocation of time on the systems and things like that. So Path is sort of the allocated version of the Open Science Grid, right? So the thing here is you get a little bit better dedicated resources than you would on the Open Science Grid. Like one thing about the Open Science Grid is many of the resources are preemptible. So your job has to be designed to uh, basically get canceled by someone else, right? And restarted somewhere else if your job gets canceled, right? So it's one of the aspects of that type of system. Where Path, there is no preemption, I don't think, as far as that I'm aware. So it's a little bit more dedicated facility that allows you to do the same types of things you would do there, but kind of at bigger scale and in a more reliable fashion over time, right? So this is another resource if you're doing high throughput computing type of workflows. Another resource to check out. Oh, and yeah, one more is the National Research Platform. So this is another distributed computing resource. In this case, it actually has a nice name, Nautilus, if you're not familiar with NRP. Um, and it's really a very heterogeneous system of interesting. Oh well, the bulk of it is a collection of essentially GPU nodes, right? So if you look at the map here, right, it's kind of counting up the different types of, how many GPUs are at these different locations and things like that. There's all different types of GPUs that are available, but there's also more recently interesting other interesting hardware. Like I know there's a couple ARM systems. There's like some Qualcomm AI accelerator stuff, I think, and some FPGAs, and even some interesting um, uh, sort of smart NICs, like network infrastructure as well, that I think you can access. So it's becoming a sort of a very heterogeneous, like it's not just the heterogeneity in the types of GPUs you can access, but in the different types of compute resources beyond GPUs as well. So it's another interesting resource to check out. Again, I call it high throughput, more of like a high throughput many task computing type of system because essentially, um, usually you're requesting like a single node or a single GPU at a time kind of thing, right? You're not requesting multiple nodes for the same job, right? That's not really possible, right? There isn't like an HPC like component that you could scale out across multiple compute resources here. It's more of like you have to sort of have many jobs that each run on their own individual GPU or maybe up to a whole node on the system somewhere. So they have also lots of interesting stuff on the AI side as well, if you're into that. So the one caveat here is, again, it's not Slurm. This time it's Kubernetes. So it's personally Kubernetes. If you haven't used it before, it's definitely a bit more overhead than Slurm. Like writing your first job script in Slurm is very easy, I think, comparatively. And then same with HT Condor, very similar to Slurm in the overall length of a job script. When you get to Kubernetes, it's, I don't know, like the example script that I showed for exercise one in the slides here was what, I don't know, maybe 15 lines of code. That would probably be like 200 as a Kubernetes job. So yeah, it gets it's a little bit overhead. It's a steeper learning curve, is what I'll say. Um, yeah, so other things, so those are actual compute resources where you might want to run these high throughput computing type workloads, or even many task computing workflows. Um, but I showed you, and as we'll look again at the exercises before we close out today, um, the job arrays, job dependencies, and job bundling. Doing that in Slurm is, you can do that all manually, but there is obviously software out there that people have written to try to make this problem of launching and stitching job dependencies together in these workflows more easy for you to do and to build your research workflow in sort of a framework. And so this next section here just lists a few of the popular ones out there that you might want to think about if you don't have a workflow manager, but you think you might need one eventually for your type of work. Um, if you're working in Python and doing a lot of um, data frame type work, hopefully you've heard of Dask. If you haven't, this is kind of the parallel version of Pandas, essentially. Um, and so this also has its own sort of built-in schedulers and task graphs of how the computational elements that you stitch together will get executed, right, in parallel and distributed across multiple resources. So it's kind of more of a little bit different than scheduling jobs per se. It's really like a single job will execute this sort of task graph to complete you know one of one overall job, but they sort of parses out nicely the sort of pandas-like workflows that you might be constructing in a parallel way. Um, Pegasus is more of a general workflow management system. So this is actually built on top of HT Condor, but it basically it gives you essentially a Python interface to develop what your job workflow looks like, right? And that Python uh, interface, right? Basically, you write a Python script and write out your workflow. And basically, at the end, when you run that Pegasus script, it generates the the graph of the jobs that need to get executed on a Condor cluster, right? And so that's what Pegasus does. And so, yeah, it's a very feature-rich, been developed for quite some time, and runs on things like the Open Science Grid and Path and things like that, right? So, and even in Access, I think I have the link here. Yeah, you can try Pegasus on Access resources. I know it has job submissions even to, I think, a few other systems like Delta AI. It might submit to Expanse right now, I think. Yeah. Oh, there it's listed here. Yeah, Bridges 2 and Anvil. Anyway, there's a few different access resources that they've integrated with where you can actually run Pegasus jobs out on those systems if you have an allocation on them. right? So if you need to think about learning how to use something like HT Condor, the next step after that is like, okay, if you need to actually build like really complicated workflows, Pegasus is kind of the workload manager for you. Other, I think I have two other ones that I see a lot of that I haven't used a lot myself, but I see a lot of people using them on our system. So SnakeMake is one of the ones I see, and mostly it's usually people in the biological sciences, I would say, who are using SnakeMake that I see, and then NextFlow as well. Both of them sort of in the bioinformatics, biological sciences um, arena. So if you haven't heard of those are two other ones that I see people like and use on our systems. They're and all of these tools here are pretty steep learning curves. So, you know, it's definitely an investment. And if you're still just learning the basics of job submission and things like that, you might want to hold off on these. But just know that there's other systems out there if you really start getting into these complicated workflows with job dependencies and job arrays that you need to sort of all link together in a sort of coherent manner. These um, workflow managers help build those graphs of the operations that you need for this many task type computing workflows and also help manage the jobs and keep you updated and which ones failed, which ones should restart, all this stuff that you need to think about when you start constructing them. Okay, so we have about less than 10 minutes now before the top of the hour. So what I'll do is stop the slides here. I'll open up the exercises and start walking them through. If you have to leave at the top of the hour because you have another meeting or class or something to go to, please do fill out the survey that Cindy will send out, or she maybe already linked to in the chat. But yeah, don't forget that if you do have to leave, that the links are at the beginning of the slides. So if you have the slide link, you can go back up to the top. Go back up to the top myself. And the exercises will be in this Summer Institute link. Oh no, did the link not? Need to update that again. I'll update that again in the slides. It's not active, the link. You have to actually copy and paste it. Okay, so let me go ahead and share my full screen. And so yeah, I'll walk through the exercises quickly. Just maybe I'll do one or two and then give you just an overview of the different tasks that you'll do once you have time to sort of take a look at them. But then also, if there's any questions, feel free to start putting them in the chat, and we can do that sort of Q&A after the top of the hour once I sort of maybe stop the demo for the exercises. Okay. So yeah, as I mentioned, this is the last version of these exercises. I sort of updated at our um, Summer Institute at SDSC held back in August. So the exercises here themselves. This is not working. Interesting. Okay. Sorry, I'm just trying to adjust so we can read this. Um, so yeah, the repo here has a few different markdown files that have sort of break up the sections kind of into what we talked about: job arrays, job dependencies, job bundling. I mentioned briefly preemptible jobs, and then sort of the resources that I just talked about, like OSG and Path are mentioned there. So the core ones where, especially the first two, have sort of worked out examples. Of course, these are sort of there's some things that you would have to change to run on, a system you might have, a Slurm system you might have access to, but it's just like your different account, maybe the different partitions and things like that. You can easily modify these job scripts and run them elsewhere. These are all designed for expanse, and there might be some like reservation attributes and things like that that we were using during the Summer Institute. So those things you can change as needed to run them, but they should be fairly complete. So let me go ahead and jump in on the job arrays. Oh, let me do this actually. So if you have access to a Slurm system, so I'm just going to use expanse. The first thing that you usually want to do is, but I have to probably download. Maybe I was smart about this. So yeah, you could download the whole repo of the Summer Institute, but that's probably a little overkill. As I mentioned in the slides, the example problem we're going to use for the job arrays and job dependencies and stuff like that is this just estimating pi calculation. So I have some code here that we'll use to run the exercises. So that's what's going to be run from the job scripts that are in the repo. So I'll just git clone that. So I've logged in, I've cloned the repo. Just explains you a little bit what's going on in the program. And yeah, I was smart about it. Okay, so yeah, so basically next, if you download the example job scripts, they should all be basically in these wget lines. So essentially, it's just pointing to the raw file. I didn't want to download the whole repo, so I'm just downloading the individual job scripts as I need them from GitHub. Okay, so now I have this 4pi directory. Just trying to make sure everybody can see everything. 4pi and the estimate pi script. So let's look at the estimate pi script. So this is that first example number 1 in the slides that I mentioned that basically uses this pi.shell script to do a Monte Carlo simulation to calculate the value of pi. And these variables don't matter too much. The S is essentially just this is like the number of bytes. This is the number of digits to round to, and then the S is the number of samples that you'll use, essentially, right? So I'll modify this script in this few examples here as I work through them, just because, as I mentioned, this was sort of set up for the Summer Institute. So there's 2 lines here that no longer are really valid. This reservation doesn't exist, so I'm going to delete that. And then the account I'm going to use is my account, which is use300. If you have access to Expanse or another system, right, you should hopefully know the account to charge the job to. And that's all I'm going to change here, right? So this is essentially setting up the initial job script to just test this simulation code, right? Albeit a very simple one. So I'm going to run my sbatch command. The job has been submitted and it's waiting. So I'll just review some things from the basic job submission. What we see here is once you submit the job, right, it's assigned a job ID, as I mentioned. I'm running it in the shared partition. It's got a name that I gave it, right, estimate pi. The state is now pending. It's running on one node. In this case, I'm in the shared nodes. So I'm just running, I've requested a single core. And this is an often question that we get is when the job isn't running yet, people will see different messages over here, right? So not sure why they do this, but essentially, right, there's 2 different pieces of information that might pop up here. When the job is running, it'll give you the node list. It'll tell you what nodes the job is running on, right? When it's not running, it's in the pending state, the in the parentheses it says reason. So what's the reason it's not running, right? So that's what the other part of that same, I don't know why they put it in the same column. It would be nice if they separated it, but um, yeah, so you see the priority below is in the parentheses, right? So that means that my job doesn't have enough priority yet to run, right? Usually this is kind of, it might take a while for the scheduler to just get to your job and then assign it a priority that's high enough to, or to see it and then schedule it. So it's an often one that you'll see, right? My job is already run in the time that I've been talking there. But the reason codes are useful if you're not familiar with them yet in Slurm, right? They tell you why the job isn't running, which is a common question. So if you have a reason code, Google what that reason code means before sending in a ticket to like the help desk, right? Because it really is a common question. It's like, why isn't this running? Like I have this string of sort of maybe an explanation, but I don't know what it means. Right. So try to Google that if you see something like that and you're not sure what the reason is why it's not running. Okay. So I've run the example and I've just listed the files um, in my home directory here. Probably should put this in a different directory, but that's okay. So here's the output file for the estimate pi, and just to confirm that it worked, the output is an estimate of pi, and then I also use the time command just to see how long it took to run, right? So this took a minute essentially of real wall clock time to run. So it's a really short job. Again, this is for example purposes, demo purposes only, just to teach you the mechanics of setting up, in this case, job arrays, and then in the next set of exercises, the job dependencies. But yeah, so we've confirmed that the job works. We've looked inside to see that we got the right outputs. Well, this explains what's inside the job script. Ran the job. Yeah, we saw the output here. So now we want to create our first job array, right? So this is a Monte Carlo simulation, right? So if I run a bunch of these, each job is going to have a slightly different estimate of pi, right? And, in the theoretical demo world here, having more versions of that same simulation, maybe I can calculate a more accurate version of pi from all of my simulations if I combine them together eventually. So again, this is using just the array attribute or sbatch array directive to index the different jobs that I want, identical jobs I want to run, right? So all I need to do is add that sbatch directive and it'll run multiple copies of the same job, right? I don't want to change anything else. I just want to roll the dice again with 10 versions of the same code essentially, but with just slightly different random numbers that are getting generated, right? So if let me just try to keep this clean, sbatch estimate pi shell, sbatch job submitted. So now you can see here, we have in the job ID category, you see, obviously we have 10 jobs now, but what's being shown in the job ID column is actually, so this is the Slurm job ID, right? Right, so this is the Slurm array job ID, right? This initial, right? So the array has the same array job ID. This is what's known as the Slurm array task ID, right? And so this is in the Slurm documentation. These are also environment variables that we'll see later, I think, in this example. But this is, essentially this number plus this number is now the Slurm job ID, right? So there's sort of three different IDs now assigned to each individual job or task, whatever you want to call it, right? But let's go ahead and see. Okay, well, I'm waiting again for priority. So maybe I should switch to the debug queue. Um, but yeah, so with if I just open the job here while we wait, oh, I didn't change it. Okay, so that's good. So you'll notice here in the output directive, right, this sbatch output, this is the name of your standard output file. And in my case, the standard output and the standard error. I personally don't usually like separating both. I usually just put everything into a single file because I don't want to look at both usually. But I mean, there's different reasons that maybe you would do that. But I usually just have the sbatch output directive. But you'll notice here I'm using these sigil terms essentially, right? These percent letter, percent letter, percent letter. What does that mean? So these are just shorthand hooks into using information that the scheduler has about the job already to name the job. So the percent %X here is essentially copy and paste the job name. So basically I'm saying name my output file after the job name dot O for just I use for output. %J is the Slurm job ID. So basically every output file that I have, I attach the job ID to, right? And then %N is the node, the name of the node that the job ran on, right? So having these three pieces of information are like pretty useful. I mean, and each output then is individually, uniquely sort of identified, right? Because we'll see a lot of times when people start writing job scripts, they'll leave this sort of output file um, with the same name, and then if they keep running into problems, they'll just keep writing over the output file as they keep resubmitting the job. And it's hard to then debug things if you don't keep a record of like what you changed and what happened in the last job and then now in this job. It gets a little confusing sometimes. So having individually labeled unique output files is very helpful, especially if you ask people like me and Nicole for help by sending a ticket to the help desk. We're going to usually ask like, what's your Slurm job ID? Where's your output files? How can I know what files you're looking at and which one is associated with which job? Right. So just a useful tip here. Now, I open the file to check something else. Oops. Let's do the me. Okay, job is running now. Okay, so I should be able to see the output files, maybe? Yes, okay. Okay, so this is interesting. Good. So you'll notice here, the output files, right, are, as I mentioned, labeled by %J, right, which is the Slurm job ID. However, usually when I run a Slurm job array, what I like to do is label it with the array ID and the array task ID, right? Like it's shown here, right? So if you notice over in the examples for the demo, my sbatch output directive is slightly different, right? I'm not using %J anymore. I'm using %A and %lowercase a, which is the array job ID and the array task ID as shown kind of here, right? So basically each of my jobs would have two IDs now associated with it. Right. But I forgot to change that when I submitted it. So here it's showing the Slurm job ID. right? So you'll see if in the example, here's the array ID, here's the array task ID, right? And that's a slightly different structure than the job ID. But as I mentioned previously, right, it's really this is the first job in the array, and then you just add the array task ID to that original job ID, and just keeps adding up, right? So anyway, so those are just the little nuances of organizing your output files and things when you start running these larger and larger arrays. Okay, so I'll fix that in the next example. Um, yeah, so these are just going to run again for a minute, right? They should be done. Uh, we'll look here at that first line. Let's see. I'm just looking at the first line of the output. Those are my values of pi. You can see each simulation is slightly different. And yeah, it's just a simple Monte Carlo. Now, in the next example, one of the other common things, in addition to running the identical types of jobs that you might want to run, um, is creating parameter sweeps, right? So if you have some slightly different variable that you want to sort of iterate over in the jobs, you can do so using the array task IDs, essentially, right? So, because it's just an index, right? So in this example, you just go ahead and do this. So I'm going to change my array IDs to 1, 2, 4, and 8. And I can do that because basically you can change the values there and list them as a list or as a range or whatever. There are some limitations on what those values can be, and I'll talk about in a second. But if they work for you, you can then start using what I mentioned, those Slurm array, uh, Slurm environment variables, right? So each job will get a unique version of, sorry, the Slurm array task ID, right? So that's what this index is good for, right? You can basically use that index as a hook into, in this case, I'm directly using it as a variable. So basically this dash B, remember, is a byte variable. So it's basically um, the precision of the sort of calculation, essentially, with 1 bytes, 2 bytes, 4 bytes, and 8 bytes. I was using 8 bytes previously, right? So if I vary this parameter sweep over the fidelity, essentially, of the simulation, that's what this is doing, right? Just by using this Slurm array task ID environment variable to actually inject it directly into making each simulation not only different because of the randomness, but different because of the precision of the calculation, right? Oh, I was going to fix this. And let me fix this. I'll submit that. And then I know there's a couple questions, I think. So I'll stop and start taking questions since it's 12:15 too. So I'll answer a couple questions and then just give you a quick overview of some of the other exercises you can work on when you get a chance. So, oh, Bob, my
Hi,
notes
hi,
are a bit
Marty.
all.
Yeah, we,
Yeah,
we
go
had
ahead.
we had one question from Brian that I think I answered, but you're the expert on Slurm, so if you want to check that and see if there's anything to add.
Sure. Yeah, I'll just take a break there and look at the question real quick. So do you have an output file specified in SBatch if the program you're running saves its own output, i.e., we support a lot of R users whose R script saves their own output already, or is this specified out strongly considered best practice? Yeah. Let me see what Bob said. Sorry. You think that R writes? Yeah, I mean yeah, it's a good question. I mean, yeah, there, many programs, right, get pretty complicated and then we'll have multiple output files, right? And each program will have their own sort of um, way of organizing data in different output files. And so you're always going to have some sort of standard out and probably standard error, or if, in my case, I usually just combine them. You can keep them separate from the jobs themselves, right? There's always going to be one of those output files. Whether or not, yeah, as Bob mentioned, whether or not the users, say R scripts in this case, or other programs, direct that output into those files, is kind of up to, I mean, you can do it, right? Um, right? If, like, yeah, in our case, in this case, I'm using a simple shell script. I also think I might use like a Python version of this program later in the examples, if I remember correctly. And yeah, I mean, these are really simple programs and not doing a whole lot of output and things like that. So it's very easy for this program to write everything just to a single output file, right? Um, in more complicated cases, there is good reasons to have different output files for different pieces of information and keeping that separate from the standard output that might be generated from standard out or standard error, right? Um, However, my point about uniquely identifying what files are generated by what job is still probably the most important part, right? So even if people in their code are writing to like different output files for different reasons as they run that, say, R calculation, that's fine. But they should still be able to use these like Slurm environment variables to label, say, output file A dot Slurm job ID, right? So that output A from running it the first time, we know it's tied to that job, right? Versus if you ran it again, now it's output A dot different Slurm job ID is different from, because you might have changed something with the calculation or the number of resources or whatever, right? You want to still try to uniquely tie whatever the outputs are to the job IDs just for debugging purposes, right? And you can still use these types of environment variables that are associated with the job IDs or task IDs to help the users organize their their work essentially, right? It's just it gets a little cumbersome sometimes, and it's a new way of thinking about it, but it really is helpful for, I think, in the long term for the vast majority of users, but also then especially when you ask for help, because it's like it's helpful to tie different outputs that were generated to different jobs essentially.
And Marty, let me add one more thing. This is
Yeah,
something that I've done in the past. Yeah, and I know exactly what you and Brian are talking about. You have this issue where there's stuff written to standard out, but then you have these other files, and that file name that says coded in your R script, your other program, may be the same for each instance. So one of the things I like to do is if I have a program that's going to be generating multiple output files and I don't have an easy way to say pass the Slurm job ID to that file, is I might in my job script just create a directory where the directory um, is named
yeah,
after the job ID and write those files there.
yeah. That's a good point, Bob. Yeah, yeah. At the very least, yeah, creating a unique directory where you dump the output for that specific job or that specific array and then subtasks. There's different ways to do this, yeah, and organize things. But yeah, at the very least, you see, yeah, some way to identify like this output file that has the same name usually as this other one if I ran the job and didn't really label anything, is helpful. Yeah. Okay, so
But
we're almost out of time, and so let me just run this last example, and then just give you a quick overview of the other things that maybe that you'll cover in the exercises. Um, and what I've done here is just what I did last time. Instead of doing a parameter sweep over the bytes, I'm doing a parameter sweep over the number of samples, right? So I'm trying to scale up the number of samples that I'm using in the job, in each job. And what you'll see is uh, a job submission failure, right? And the exercise is trying to, demonstrate like not only why this went wrong, but how do you get around it, right? And I'll leave the how you get around it part to you following up. But the reason the job submission failed is, as I briefly mentioned a few minutes ago, the array indices in the SBatch directive can't be anything. There are limitations, and these are configurable by the system administrators, essentially. Essentially, they control how large your arrays can be, right? So on Expanse, we limit array sizes to 1,000. So you can go from 0 to 999. So you can use any index number between those essentially on Expanse, right? So I can easily launch 1,000 jobs, right, on Expanse, and it'll run that array, right? We actually allow on Expanse in the shared partition up to a little over 4,000 jobs. And so you can launch like four of these 1,000 um, 1,000 job arrays essentially, right? So that's, if you have a real high throughput workload that really does need that kind of scaling for really tiny um, jobs like this, you can do that, right? But there are these limitations of like how big the arrays can be. This in particular is actually to in this case Slurm, because Slurm is somewhat sensitive to the total number of jobs that the system could run itself, right? So there's like a maximum number of jobs that can ever be sort of submitted to the system to for the scheduler, right? That's controlled by the system administrators as well. That's why there's these limits on how many jobs you can have per partition, and just trying to divide up the resources um, fairly amongst the users for the um, different types of partitions and compute resources that we have, is why these limits exist, right? Um, but things like I remember I was at an HT Condor workshop once, and they introduced a new feature for their job arrays, where they submitted the developer submitted 1 billion jobs to to their HT Condor cluster with this new feature. And so they had some smart tricks of like how they manage all of those tasks in that job array, where they can basically submit, way more, tasks per array than something like Slurm can. Um, I haven't actually tried that myself. I'm still a little bit scared to, but in theory, I think that feature is still in HD Condor where you can submit really, really large job arrays. Um, anyway, that's just kind of a side note. Um, okay, so yeah, so there's a few more exercises. Again, you have to figure out how to, still do this parameter sweep, but without using the indexes that you might want to naturally use. And so there's some examples about that. I think that's almost, oh, and then there's some ways you can throttle like how many jobs that, I just submitted a job. Oh no, I submitted 2,000 jobs now. Um, um, too many jobs. Maybe you don't want to run all 1,000 at the same time because, for example, right now I'm now writing like 2,000 files to my home directory, which probably isn't great if you're constantly writing to your output files, if that's your type of I/O pattern for the job you're using. So you might want to throttle the number of jobs that are running simultaneously at any time, but you still want the convenience of submitting just like large batches of jobs and let it go, right? So there's a way to throttle jobs, and that's the last part of that. On the job dependency side, what we do basically is you work through just the mechanics of creating the job dependencies by taking the output from these sort of array jobs and then attaching a analysis job after that sort of combines all of the results, right? That's sort of the main task of creating this first job dependency. So that's for the main thrust of the job dependency exercises. And then job bundling. It mostly, yeah, it does walk you through some of the examples of the different techniques using the same stuff that we've done here. Here, I think I changed over to the Python version of the program. That's the only difference. And it talks about using backgrounding processes with the ampersand sign if you haven't used that before. Using task set to lay out which version of which copy of that, you know, subtask that you're bundling into the same job, which core it'll run on, and why it fails in this case, and so on. Um, so it just walks you through some of these basic initial steps into how people do job bundling. And yeah, I haven't worked out all the exercises for the NUMA CTL, and I think you could probably run the MPI based version. Anyway, it just talks about some of the other examples of different ways that people do this bundling problem, and why you would choose one for the other kind of depends on your preference and what you're sort of comfortable with using, and what maybe your program is actually doing. Like for example, in this case, I have a hybrid program where it's sort of, I mean, a parallel version of the Pi program here, where each process actually uses a couple different cores, and so it can get complicated how you pack, these jobs into a single compute node, for example. Um, anyway, I think we're, yeah, just about out of time. So if there are any other questions that people are here sticking around, happy to answer. But if not, we're sort of done for the day.